we talked about how currents experience a force when placed in a magnetic field. That currents, wires that have currents flowing through them can experience a force if they are present in a magnetic field. Well, contrast to that, currents are affected by magnetic fields because currents actually create magnetic fields, as do all moving charges. I mentioned in previous videos, magnetic fields exist because of currents. And at the atomic level, you can think of the electron spinning around the proton as a little current flowing around the proton, giving the atom a magnetic field. So how do we know how strong a magnetic field is generated when a current flows through a wire? Well, for long, straight wires, we have the following equation. If you have a long, straight wire, the magnetic field strength around that wire depends upon a constant called mu naught, the Greek letter mu, mu. Mu naught is referred to as the permeability of free space. It's a universal constant in physics. It is equal to 4 pi times 10 to the minus 7 Tesla meters per ampere. So that is a universal constant. It's on your constant sheet. This can be put in your notes. Whenever you see mu naught, that's what mu naught is. Just like epsilon naught is a universal constant, like Boltzmann's constant, the gas constant, the gravitational constant, the big G for Newton's equations for gravity, pi, all of these things are fixed values. So mu naught in SI units is equal to 4 pi times 10 to the 7 exact. It has pi is in there, so it's an irrational number, but you can go at as many significant figures as you know pi. It's mu naught times the current I, so no current in a wire, no magnetic field generated by that wire, over 2 pi times r, where r is the distance from the wire. So if you imagine this dry erase marker as the wire, r is how far away you are, perpendicular distance from the wire. This gives you the magnitude of the magnetic field around a long, straight, current-carrying wire. So if we imagine a wire going into the board, imagine a long wire going into the board, a magnetic field will be generated around that wire, having the same, since the current is the same throughout the entire length of wire, and mu naught is a constant, the magnetic field strength falls as 1 over r. So near the wire, the magnetic field strength is going to be fairly strong, but the further you get away, the weaker the magnetic field, which means that the magnetic field is going to be spaced out more. The magnetic field lines will be spaced out more than they are nearby. So the question becomes, again, magnetic fields, I've just drawn the dotted lines here to show you where the field loops would be located. To know what direction the magnetic field is flowing, we need to use the right-hand rule, but it's a new right-hand rule. So this is version number 2. To determine the direction of a magnetic field along a long, straight, current-carrying wire, it's actually pretty simple. Take your thumb, point it in the direction of the current, and then grab the wire. Your fingers curl around in the direction of the magnetic field. So if this wire is going into the board, my fingers curl around clockwise, so the magnetic field here goes around clockwise. So on this side of the wire, the magnetic field is pointing out. On the top, above the wire, the magnetic field is pointing to the right. To the right of the wire, the magnetic field is pointing down. Below the wire, the magnetic field is pointing to the left. If the current is coming out of the board, if I switch the direction of the current, then when I grab, here's the wire, current is going this way, when I grab the wire, my fingers go around counterclockwise. So the direction of the magnetic field will be counterclockwise. So if I ask you, what is the magnetic field some distance above this wire, say 10 centimeters above the wire, let's say the wire has a current of 1 ampere, you can plug that information in. 1 ampere, 0.1 meters, that's 10 centimeters. That will give you the magnitude of the magnetic field, and then you can use the right-hand rule to figure out the direction. So at 10 centimeters, let's say this is 10 centimeters, the magnetic field is pointing to the right and it has some magnitude of blah. And you can punch that into your calculator to figure out what that is. So, again, this gives you the magnitude of the magnetic field around a current carrying wire. And the right-hand rule number 2 gives you the direction of the magnetic field, the direction of the loops take as current flows through that wire. So rather than, again, fingers in the direction, pushing down and having your thumb represent like the magnetic force, here, your thumb goes in the direction of the current, and then when you grab the wire, your fingers will wrap around in the direction the magnetic field wraps around the wire. What if a wire isn't straight? How do we find the magnetic field near a wire that may be curved or turned into a loop? Well, to do that, what we can do is treat little tiny segments of the line as being straight. So if we have some curved wire, we can pretend that that segment is a small straight wire, and this segment is a small straight wire, and the next segment is a small straight wire, and just add up a bunch of very tiny, small straight wires together and figure out what the total magnetic field is. This is called the Biot-Savart law. I'm not pronouncing that correctly, I'm sure that's French. This requires integral vector calculus to do. So it's something that is done at a 300 level physics level where you have, vector calculus under your belt. None of you are in that position. We are not going to do this, but I just want you to know that it is possible to calculate the magnetic field around objects that aren't long straight wires. Now, for example, a current carrying circular loop of wire. So imagine we have just a loop of wire carrying some current I around in a circle where the wire has some radius r, and I want to know what the magnetic field is at the center of that loop. Well, if I know what the radius of the loop of wire is, I know how much current is flowing through it, I can calculate what the magnetic field is at the center of the loop using this equation. So the magnetic field at the center, not anywhere else, just at the center, is equal to mu naught, which again is the permeability of free space, the constant 4 pi times 10 to the minus 7 Tesla meters per ampere, times the current in amperes, divided by 2 times the radius of the object in meters. And that will give you the magnetic field strength out in Teslas at the center of the loop. Well, the center of a loop isn't really a useful thing to study in physics, but there are objects called solenoids, which are just basically long stretches of many loops compressed together. Think of it, again, like a slinky. A slinky is the shape of a solenoid, many loops all tightly compacted together. A solenoid is a useful electronics circuit element, which we'll talk about more later. A solenoid is a long coil of wire with many turns or loops, and the magnetic field inside a solenoid is given by this very simple equation. Mu naught, which again is the permeability of free space, times small n, which is the coil density. So it's how many coils do you have, if this is length L, for the solenoid, how many coils do we have? Well, in this example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So big N is equal to 13. And let's say that this is 30 centimeters. So small n is 13 divided by 30 centimeters or 0.3 meters. It's the coil density. It's not the total number of coils, that's big N. It's the total number of coils divided by how long the solenoid is. And then times the current in the solenoid. Once again, no current, either for a single loop or for a solenoid. No current, no magnetic field. A magnetic field exists in a single loop of wire or near a wire or in a solenoid only if current is flowing through that circuit. So here we have the magnetic field for a single loop of wire, and here we have the magnetic field for a solenoid.